Good afternoon, everyone. And in my case, good evening. I'm joining you from Paris today. We're so excited to host the LEAP Center here this evening to talk about, or this afternoon to talk about some of the exciting work that's developing there. I'd first like to thank the Columbia Business School and Bruce Kogut for providing the physical space today, although most of us are joining online. But we appreciate you providing access to your wonderful facilities and helping to coordinate this, in addition to Alexis with the Data Science Institute for helping us coordinate this, which actually came together on pretty short notice. I am Dr. Courtney Cogburn. I'm an associate professor in the School of Social Work, and joining you with two hats today, one as a co-director of the Computational Social Science Working Group, along with Bruce Kogut, who's the Sanford C. Bernstein and co-professor of leadership and ethics at the Columbia Business School, as well as faculty in sociology, and Augustin Chaintreau, who's an associate professor in computer science. We work together to organize the initiatives related to this working group. I also join you with the hat of a member of the LEAP Executive Committee and helps to coordinate this effort. LEAP is a newly launched NSF Science and Technology Center. LEAP stands for Learning the Earth with Artificial Intelligence and Physics, and is a cross-institutional collaboration between Columbia, NYU, UC Irvine, Teachers College, University of Minnesota, as well as others who have partnered with us on this effort. One of our, I want to highlight one of our executive committee members is Vanessa Burbano. I'm not sure if she's able to join us this evening, but she's faculty in the Columbia Business School. Yeah. And our, are you there, Vanessa?
Yep.
Hi. She directs our corporate engagement efforts. And then on the panel today, we have our director, Pierre Gentine, who is also a professor in earth and environmental engineering, Tian Zheng, who's our chief convergence officer and education director, and is also professor and chair of statistics. David Lawrence, who is our NCAR model development liaison, and is also a scientist in the NCAR's Climate and Global Dynamics Laboratory. And again, myself and my role in LEAP is our Chief Equity Officer and Knowledge Transfer Director. So we're here to learn about what LEAP is doing. We think that several of you who work in computational social science generally, who work in climate modeling specifically, may be interested in the efforts that are happening. And I think we're largely and on the LEAP side, interested in sharing what we're doing and developing, potentially exploring opportunities for collaboration, points of synergy, etc. So that's the general focus of the event today. I'm going to hand it over to Augustin, who will provide a few brief opening remarks and get us started with questioning of our panel. I'll stop sharing my slides and invite you in the name of community, if you feel comfortable doing so, turning your cameras on so the audience in person can see you, but no pressure to do so. Augustin?
Okay, hey, thanks for coming. I think in the spirit of getting started, we all want to hear about LEAP. I was chatting with people, in the elevator. Everyone is coming with lots of curiosity, learning how the computational social science can get involved. I think it works. Yes. I also wanted to just add, to the mix of discussion, in the birth of computational social science and in the birth of computer science itself, there were grand quests of, impossible challenge, sometimes that we even show that are impossible. The P = NP, of course, is one of the founding moments of computer science, and also the difficulty of understanding small world navigation has been at the beginning of computational social science. So I'm also very interested to hear about what you think of theoretical limits and impossibility results, either with physics or with artificial intelligence that are brought in scientifically to that. But that's just to add to the point that I'm sure you're going to tell us about LEAP. So I just want to get started on hearing about it and And I think after that, Courtney, you also have some more questions to add. So we get the panel to sort of probably present Lib to us, which is sort of the main focus of the event. So Courtney, are we going to start?
Yes, I don't know.
Yes.
I don't know if the panelists want to address your question.
Well, I guess
comment.
The main question is probably introduce Lib to everyone, since there's a lot of curiosity about it. So that was probably where we start.
So I'll ask to the panel, why LEAP? Why did you work so hard to pull this effort together, focus on climate projections? Why is LEAP necessary?
So maybe I can answer this one, maybe as the director. So maybe like moving backward in time, a lot of that at first, at least from my personal interest when we started building the team, was more from the research and science perspective. Like we were thinking, there's like this issue in climate modeling. I mean, of course, climate modeling has been going a long way. I mean, there's been a tremendous progress, and Dave Lawrence is here to witness a lot of that. But still, when you look across, we are not that confident in terms of the projections we're making, right? So there's a huge amount of spread across different, what we call projections. So basically the forecast that we have of climate by, say, 2100 or 2050. And that really translates into some sort of difficulty to adapt, right? So if you just say that climate change is happening, or, how do you adapt to that? And that was kind of the question. So how could we actually kind of reduce that uncertainty? And here, maybe many of you are from the business school. So in finance, that would be kind of similar to volatility, right? Volatility is uncertainty, so it's a cost, right? So that's exactly the same here. And that's a huge cost for society. If you could narrow down that range, you could actually make it much better. You could make it more efficient. You could also invest your resources much, much better. So that was kind of the original kind of motivation for that, and a lot of that was in terms of the research. How can we actually improve climate modeling, etc. On the way, I mean, we started building up that team, and and then it became very clear that you also need to be starting to have a discussion. So we have a wealth of data that goes basically unused. We have satellites observing the Earth and the climate pretty much every day, right? Even geostationary satellites every hour, right? And a lot of that goes unused, So the question was, how can we actually use that wealth of data and make it really efficient and use that to improve those climate models? And it also became very clear that to do so, you really need to create this convergence. So that's very much what Tian is actually leading, that convergence between data science on the one hand and then climate science. We don't really have experts in the room right now that can actually do those two things well, right? So we need to train a new generation of scientists or people that can actually do that, and there are very, very few people that can do that right now. So there's a huge opportunity there, not just from a climate modeling perspective, but a lot of people also on the business side. You could say a lot of people, you have lots of startups, lots of companies that are actually very interested in that type of business, at the interface between climate and data analytics to a large extent. And then yeah, go ahead.
Go ahead, Pierre.
No, and I was about to say, I mean, actually very much linked to you, Courtney. The last component of that, what became at least very clear to me, that's more of a personal feeling, is that the knowledge transfer. So how do we actually get that data to a much broader crowd, to be much more inclusive, to not make it a niche, right? Because climate modeling and climate change has been kind of a niche, but it's affecting everyone, right? So the question is really, how can we make that data, and how can we make those projections, especially if they are better, how can we make that available to anyone? So you could be in the middle of like a small village and you could have a laptop. Can you have access to that information? And a lot of people want that, but it's just, we don't really have that pipeline. We don't have that information. So that's a huge gap that we are also trying to fill, if that makes sense. And Courtney, sorry.
So one part of improving the shorter term projections is one, bridging climate science and data science in a more formal way, right? You have scientists and scholars who have been working across or at that intersection for some time, but also improving the pipeline of people who are trained formally to work in that space. And you're also saying there's a lot of unused data that we're not leveraging that could be integrated in a more meaningful way, more useful way to help improve these projections as well.
Exactly.
And yeah, and so that's a huge undertaking. So what are, there's the ideals of that, right? The big sort of overarching goals. And then there are the most practical, viable places that we start. Tian and David, what are some of the most pressing scientific challenges that LEAP is prioritizing? What are we trying to address first as our starting points?
I can speak from where I stand. So I'm a statistician by training, and I like analyzing data set as part of my research, and LEAP have a lot of that. And also we're doing a lot of research education integration, try to bring interesting climate research questions into the classroom of data scientists, and have climate science students and data science students work together to understand how machine learning can improve climate projection. During the process, one thing I think is in particular relevant to this group, the computational social science group, which I also is a member, is the problem setup. Like I think sometime when we do research, we just inherit the research question. So we set up the research question in certain way, you know, there's a training data, this is testing data, and we have certain algorithms we need to improve, and that's it. When you have people from different disciplines in the same room, like Pierre said, like when the convergence happens, people need to discuss why the problem is set in a certain way, why we're analyzing the certain way, maybe even earlier, where did the data come from? Say, for example, when we have sea surface temperature from the past 200 years, where did the data come from? Where did the data, how did the data get to the current form? All these questions may become second nature to climate science students, but for data science students, they're really important questions. So during the process, we talk about the data, then we start to realize that the data are imperfect, the data have biases, doesn't necessarily have, some data doesn't have global coverage. And when you have data doesn't have global coverage, should we be concerned about the output of the data? How do we quantify the impact of the data issues in the subsequent data product? Should we talk about uncertainty quantification? How does the uncertainty quantification trickle down into decision-making process? So these are not necessarily the question we are solving, but they're good questions we should be asking at the moment. And so my project for the first year for LEAP is to understanding how deep learning algorithms have been used in creating representations of climate dynamics, and to evaluate them. Like, I think to me is even an open question, how do you evaluate such representations? When you have representation creating a machine learning algorithm, you usually rely on subsequent predictive challenges, predicting tasks to quantify the performance of a representation. So so that's my I think it's some low-hanging fruit for statistician and machine learning to engage in LEAP research, is to apply their algorithm to the data set and understand how this data product can be used to support decision, to support policy, to support subsequent analysis, and then to discuss whether the current metrics and evaluation used are natural, or understandable, or trustworthy for the users, for the consumers. And then to answer Augustin's early question, what does it apply to the computational social sciences? I think a lot of, I truly believe that we start to seeing a turn of time where the human society will start to have more active interaction with the climate, with weather in a more interactive way. Like we start to see our life being affected, our planning of the site being affected by climate change. So I think there should be more and more discussion about if LEAP is able to create refined and projection of climate, how would that affect human society, behavior, policy, finance, business, urban design, all those things will definitely have, can be impacted by climate change. And if LEAP is able to create, to start a conversation in that direction, I think there are a lot of overlap here.
Yeah, thank you, Tian. And David, you've been working in this space for quite some time. What's different about the scientific challenges that you're taking on with LEAP specifically? What's the potential here, and what are your priorities?
Yeah, I mean, I think it might be helpful here to just take a little bit of a step back and provide some context, just for anyone who doesn't know. Pierre introduced briefly a climate model, or we call them often Earth system models these days. And there's about 10 to 15 Earth system models that are being built by scientists around the world, major institutions around the world, trying to build these models that make predictions of the climate system. And LEAP is targeting improvements in 2 of these models. The one is called the Community Earth System Model, which is maintained by the National Center for Atmospheric Research, where I work. And the other one is the NASA GISS model. I see Gavin Schmidt is on here. He's a prime person in the development of that model. And so we're trying to improve these 2 models. Now, of course, there's a large group of scientists from all around the world that have been working to improve these models for decades now, and they are getting better. We can show that, but the progress is really slow. It's painstaking, it's painful, it's 2 steps forward, 1 step back. And so the goal of LEAP is to try to accelerate that progress, because the needs for the prediction and the accuracy of the predictions is so large. We need to accelerate the progress. And so the idea within LEAP is that we can accelerate that progress by making better use of these vast and growing Earth observations and high resolution models to help improve these models. So these models are intensely complex. It's really hard to get across how complex they are. But the scope of I try to put the scope of the problem through people sometimes, and within CSM, the model that I work with and help lead the development of, you can argue that there's 150 people in our lab all working on developing the model, and there's about 500 people, I think, depending on how you count, across the nation of the world trying to build and improve this model. And so then where LEAP comes in is we're going to take a new approach in LEAP to bring data more into it by using machine learning methods. And I'm not an expert in machine learning. I'm an expert in model development and terrestrial science in particular. But there's several ways we can do this. One is to try to get at better representations of what we call unresolved processes. So a typical grid size for a climate model these days is about 50 kilometers to 100 kilometers across. So that's a very big area still. I'm sure you can imagine that. Probably all of Long Island fits within 1 grid box, maybe 2 if we're lucky. And so a lot of things are happening at scales smaller than that. And so one thing we can do is run really high resolution models for just small domains with all the physics that we know about in the system, and then see what that model, a high resolution model, says. Use machine learning to try to identify, what are the factors that are controlling cloud formation, for example, which is really critical in climate change. And so then use that information, develop new equations that we can then move into the Earth system model and better replicate processes. And I won't go into too much more. I just say that that's resolution. The other big challenge is things that we just don't have like strong physical basis. For example, biology, ecological processes. There's not fundamental equations that describe these things. And so we can use machine learning to try to learn what are the relationships between environmental variables and plant growth, for example. And so that is another way we're going to try to accelerate the advances in Earth system models. Stop there.
So we're trying to, just to sort of summarize, because not everyone.
I think Pierre had he raised his hand, so I just wanted to make sure.
Yeah, if I may just add, I think what Dave said is great, you know, and I think also we shouldn't say that, and I mean, that's the hope, you know, that AI could actually really help, you know, and there's also going to be some new algorithms, but I think a lot of this approach is also with a lot of humility, you know, because we don't know if that's going to work, right? So, and a lot of that is going to be a first time around, right? So we need to be very careful, and exactly as Dave said, you know, it's going to be maybe one step forward and then two step backs, you know, because you might be improving parts of the models based on some particular metrics. Maybe your temperature is great, but maybe your rainfall is degrading. So meaning that, you know, it's going to be a long process, a long journey, you know, and that's what we expect. You know, it's not going to be changing the world. And, you know, there's, again, like so many scientists that have been working on those models for a very long time. So, but we expect that maybe at first for like sub processes, specific things where we believe there's going to be potentially a leap, or there could be some leveraging, we believe that there could be some value there. And then we want to move forward. You know, if that works, then we were going to expand and move on, you know, but we want to be very careful in the way we want to implement that, if that makes sense.
And why now? Why is this more feasible, possible now than at other points in history? Are there some advances that have happened in data science or on the climate side in terms of access to data that have changed even the possibility to start exploring, you know, some of these questions?
I mean, I'm sure Tian will have a lot to say there, but I think it's a convergence that we are seeing across many different fields, you know, from the biomedical field to the social sciences, where it's this convergence between having access to a lot more data, right? So there's a lot of data out there, and actually in the environmental sciences and in climate in particular, we are very data rich, right? We have a lot of data. In fact, a lot of people are envious in terms of how much data we have, right? I mean, again, remote sensing is crazy, like petabytes of data every single day, which is an issue actually at some point. So that's one thing, like getting the data, progress in the algorithms, and how you can actually use efficiently those data streams, right? I mean, that has really created a revolution in machine learning. You know, like neural networks have been around for a very long time, you know, since like the 80s or 90s, you know, but there was like some plateauing for a very long time because they didn't have the data to actually feed them and the algorithms to properly use that. So that's been a big change as well. And then kind of a third kind of nice convergence as well is the fact that a lot of the codes, for instance, is becoming open source. So a lot of people can contribute to, for instance, the community or system model. NASA is also moving in that direction. So people can really get involved, you know, whereas before it was a bit more difficult, you know, it was a bit more opaque. You had to be there. You couldn't really get access to the code. So that's been a very nice improvement in the community. And finally, I would say a lot of the data infrastructure as well, right? There's a lot of development in terms of getting access to the data on the cloud, computing on the cloud. So you don't need to download petabytes of data, which you cannot do anyways. So that's, I mean, I think those four things are kind of happening at the same time. So that's really helping towards that revolution, we hope.
And speaking of data infrastructure, how is LEAP dealing with that? You know, this volume, this massive volume of data, is LEAP tackling that specifically? How do you manage and store that amount of data? How do you support the analysis of those data? What is LEAP doing in that arena?
I can
Yeah,
try
you
to
could. I was
answer.
about to say,
I can, even though I'm not the right person.
Ryan, right.
We have a person on the team who's really passionate about creating a community around a cloud platform. So he is a core member for a project called PanGeo, which is a cloud-based data sharing platform and also computational platform. For LEAP, we're going to take that to a next level called LEAP PanGeo, which is currently enabled by the Google Cloud. It will start as a Jupyter Hub with different tiers of access that we are hoping to open this up to the entire community. And we're also trying to use that to empower research and collaboration. I think Pierre alluded to a part of that. The reason why the moment is right for such a convergent collaboration, where you saw on Courtney's slide that involving multiple institutes geographically distributed across the US, is because we now have the cloud for us to be working on the same data set and same algorithm at the same time, enabled by Zoom and communication technology and our newly acquired skills over the pandemic. So the LEAP is hoping to use the PanGeo to achieve two things. One is the collaboration in computational intensive research. Second is to try to use the PanGeo to share the products, the algorithm, the machine learning methods more openly and in an open and reproducible way. So that's at least my understanding. So currently the PanGeo is live, and we are putting final touches on the protocols of granting access to different potential users, from community affiliates all the way to researcher, including a process to support courses that would like to leverage the data, the computational algorithms, and then the computing platform LEAP has to offer.
Yeah, and I'll just add to just sort of further highlight that, in the spirit of being open source and open access, we're really trying to make that as accessible as possible and put it in and make it usable for as many people as possible, which is its own challenge. Can you all speak to, and shifting gears just a little bit, because I think it's very meaningful that LEAP has placed so much emphasis on the educational components, broadening participation, diversity, equity, and inclusion. Why is that so critical to the work of LEAP, right? We're going from deep learning and algorithms and integrating these different types of data. Why are those more social factors? And I think, that speaks further to the relevance of computational social science. Why are those factors so important for what LEAP is taking on, and for climate science in general?
I can start.
Yeah, I was about to say. Yeah.
So it's a great question, and then definitely have a lot of dimensions. The first dimension is that both climate science and data science have a lot of room for improvement on the DEI front. So we are hoping by create a convergent science through LEAP that we are also creating a collaborative and inclusive culture at the center to create multiple pathways, talent pathways for more diverse students to enter climate science and data science through the education activity and the research programs LEAP has to offer. So that's on the diversifying the workforce, the research workforce. And also, I think climate is a topic that touch on every single aspect of our life. So it's important to have diverse perspectives at the table when research is being discussed. Especially in discussing how we identify the research priorities and how to communicate the research product to the public is also an important aspect that can have a social science angle. How LEAP research can be viewed to have a social impact? Like, how can we communicate and how can we connect with the potential users of LEAP products so that they can see what we produce have a social impact is important. And then it definitely invite active conversation and research.
And if I may add to that, I think there's also a very clear connection, between climate change, social justice, inequity, where we know that for a fact, and there's been many studies showing that climate change impacts the most vulnerable the most, and so that's one thing, and at the same time, they are the ones that are contributing less to climate change. In fact, the richest you could look at the numbers, it's like an order of magnitude in the US in terms of the contribution to climate change, in terms of the emissions. So, there's really this this huge discrepancy between the emissions and the impact, and however, everyone is being touched and everyone is emitting, and we need to reduce those emissions, and we need to make sure that people can adapt, and that in the long run that they can also what we call mitigate, that they could be able to reduce the emissions and ideally even go to net zero. So it's not, again, a niche problem, right? Climate change, it has to touch everyone, right? So we cannot just make it appealing to a very small community. So it has to be a broad view, right? And it has to be reflecting the broader community. So I think that's very, very crucial. And if we were to miss that, I think we are like missing the whole point, Yes?
Courtney, if I can ask a question?
Yes, please, go ahead.
Thank you.
So thank you so much for talking with us about this, and it's extremely interesting for us. So I want to ask two questions. Let me ask first a very simple question, but it's probably hard to answer. How much of the causes for the elements which are responsible for climate change are natural? Animals or forestry decaying or things like that, as opposed to things which we can directly attribute to human actions. Do you have a sense of how that might work?
Yeah,
out?
it's extremely small, right? I mean,
what's extremely small?
The natural contribution, right? The natural variability to climate, to climate, right? I mean, so a lot of that was even historical, like land use, land cover change at first, before like
right.
emissions from the Industrial Revolution. And then moving from there was mostly the Industrial Revolution, the greenhouse gas emissions. For a long time, one thing that people don't realize is for a long time, we are lucky to some extent. There was a lot of buffering in the system where you had aerosols that were playing a big role and buffering a lot of climate change for quite a few decades, right? In the meantime, you also had a lot of storage of heat, for instance, in the ocean. And now we are like seeing that big time, right? I mean, now every year you can see that there's going to be more and more extreme events. So, I mean, it's happening right now, and the causes are completely clear here for sure.
So let me ask a second question. I don't mean it to be, I don't mean it to be too provocative, but a little bit provocative is probably good for an audience. So
tend to be the same.
When I hear about the CSS part of it, there certainly are issues of social justice and unfairness and particularly in outcomes. Processes are a little bit different about this, and processes might also include things such as the choices made by governments or the choices made by people, the way cities are managed. And so you have people like Scott Barrett, who does integration. I should know these people, you have people who think about the behavioral consequences of saying no. Elke Weber over at Princeton now used to be here as well. And then you also have people who think about the way in which investment actually occurs. So there's a market on energy, even though it may not be directly traded sometimes, so that we do have more and more carbon trading. But we also have things where you can back out the discounts being put to stock prices, et cetera, on the probability distribution of what you think is going to happen to that company and elsewhere. And this is a much more sophisticated sort of questioning about what it means to be computational social science on that. And I don't want, this is the provocative part, but let me turn it around and say it in a way which opens up a response to you. Is, well, what are you doing there? Because I haven't heard anything about that part of it. It's like lots of data. I understand that. Part of that data could be from other places, such as stock market data. Just give an obvious example. But what is the reach out for people who do that pretty well, and how is that going to be affecting your work, which I guess is partly forecasting going forward?
So you mean using their data for our center, or the converse, right? That they could use
both ways. But certainly, given the account I just heard about the use of social science data, including the economic data I mentioned, how is this going to be? What is the contribution of this area to the work you'll be doing?
So that's actually a great question. So when we started the whole enterprise of the center, there was this discussion, you know, like how much of the human component should we have and how much of the physical component should we have? And we thought, okay, that's relatively a large funding, you know, but to some extent we want it to be self-contained, you know, so we really targeted just the physical component. Doesn't mean that it's actually very clear that the human component and the socioeconomic component is huge, you know, especially at longer time scales. But we said, okay, let's focus on when and where the physical processes and biological processes are going to be critical. So basically the intent was to say, we are focusing on a time horizon going to 2050 to 2060, where we believe that investment is going to be important. You know, we have a little bit of a view there. And then from 2050 on, that's really where the socioeconomic background is going to be critical. Like, do we invest more into renewals? What is growth like, you know, in the future? And so this is something that we assume is given to us, you know, but we are not really working in that space, you know, if that makes sense.
So if I can just follow up on that, you know, as a naive person, I'm a little shocked by that. That's because I'm naive, so I want you to. So I'm Bayesian updating by your model you're using on this. So how could it be possible to leave out the human component of this when that will be determining all kinds of policies which will be affecting the climate? Whether, you know, people even basically accept the proposition, which is deeply contested in this US about climate change, right, what policies should be, to the choices of instruments which might be used, to the economic opportunities of firms to come in, because all this money is not going to be coming from governments alone. It's going to be coming from private sources. So I don't get it. So do you have arguments about this issue about leaving the human out, or
no? So maybe there was some misunderstanding. I'm not saying we are leaving that aside. It's just that the focus of the center is just on the physical space, right? And they are very good people looking at the socioeconomic component. What we do, and that's basically how that those models, so what we call an Earth system model, but let's say a climate model is being run, is we prescribe typically the greenhouse gas concentrations, not even the emissions, typically, even though you have some of them that have the emissions. And so we prescribe that, and then we look at what is the response of the planet to that. Like, is there a change in temperature? Is there a change in rainfall, etc.? It doesn't mean that it's not important. I'm actually personally very interested in that, and I feel that there's a lot of discussion that can happen in terms of also that connection between the two. Like, can you inform policies, you know, through this coupled socioeconomic / physical system? And I think we can start from like simple, idealistic. So that's actually, I have an intern now looking at those things. Like, can you define optimal mitigation strategies? Like, can you define optimal policies? You know, I think we can actually start doing that now. And but we are still quite far from actually being really able to be able to actually do that in practice. I think those things are highly complex, also like in terms of the numerics. So that's why it's not that easy as well. But I think you're right. It's very, very interesting, and you have many constraints, right? You have physical constraints, the economic constraints, logistical constraints as well. Like, you want to take out CO2 from the atmosphere, carbon. Where do you put that? You know, so you have many, many things that are coming into play, and those are very interesting. What are the main constraints that we have? You know.
Right. So if I may want to offer a perspective of what LEAP is trying to focus on, and also I saw Dave's hands up. So Dave, you want to go
his hand
first?
was
Yeah,
go ahead.
I can sort of clarify this a little bit too. I think, you know, the way within LEAP, we're not focusing on the human side, but within Earth system modeling, there's a whole community of researchers who are building scenarios of future socioeconomic growth patterns that link energy, water, land, climate needs to meet the needs of a future population, and going through a whole range of different assumptions about whether we're going to live in a conflicted world or a collaborative world, or a world that emphasizes sustainable development. And so that community of researchers are providing scenarios to the Earth system scientists like myself, and then we take those scenarios and then run them through the Earth system model to assess the climate consequences of different socioeconomic scenarios. So there is a feedback, and then we can go back and tell them, say, well, you were assuming that we could grow crops in tropical sub-Saharan Africa, new crops in out at year 2050, and we can say our models are suggesting that the climate will not be suitable for crop growth any longer, which is going to, then they can take that information and realize that that's going to lead to conflict and make other, scientific discoveries along that line. So, and there is a sort of a somewhat of a two-way interaction, but we definitely get that information from this community of scientists, and then we run those scenarios for them to understand the climate consequences. So it is being taken into consideration.
Thanks, Dave.
So Leap's focus is learning Earth with the reason why AI is brought in is that the traditional way of running Earth system models using the traditional numerical method can be very computationally expensive and slow, which create a sort of a bottleneck for the capacity of how many of the scenarios that Dave just mentioned can be run in a reasonable amount of time. And also when you create a simulation out of Earth system model, based on my understanding, I'm still learning, is that you need to create a grid over the Earth. You can only, it's a grid point, right? So how fine that grid point is, how much resolution you can have on a grid point is also being limited by the computational power and the data storage, and how quickly you can emulate all these different scenarios. So that's why Leap, the problem Leap try to solve sounds simple in a way that we're only trying to make the grid finer and then the projection more certain in order to be able to support other research, but it's actually a very hard problem. Another thing that relates to your question is that, for example, like what Dave described a scenario where people want to understand in 2050 what kind of climate you can expect to have in certain region of Earth. But the current scenario is that you can make projection, but there's a tremendous amount of uncertainty in the projection that can run from like totally okay, nothing gonna happen, or a catastrophic scenario, and then it becomes inconclusive for the researcher who are looking for a more certain, more refined scenario. And also, I can offer another small example is that I'm running a course called Climate Prediction Challenges. The first one involves students exploring historical data for hurricanes. So some students connect that with socioeconomic impact of the hurricane. And so usually people cluster hurricane based on their trajectories and their categories, their wind force, wind speed, etc. And the students actually clustered the hurricane based on time, population impacted, economic loss impacted, and they were able to create profiles of those hurricanes, where they were born, which part of the season they were at. It was a very interesting insight.
So to just put a finer point on the rich responses that you're all providing, and let me know if I'm on track here, is that reducing that spread is critical for lots of different social and economic factors, migration patterns, food production, the possibility of restricted resources and the ways in which that might contribute to conflict of various sorts. So being able to more accurately predict temperature globally, right, becomes critical, for example, to improving our understanding of implications for the social factors. And it also sounds like improving these projections are also important for issues of social equity. Who's contributing most to this harm and damage? Where might there be variation globally? Where might there be variation even within a city, say, in terms of global temperature? And becoming more precise helps us understand, who's going to be most vulnerable to particular changes as well. Does that sound like a fair summary of the points you all are making?
Yes, I think that's a great summary. And maybe if I could also like summarize that in a different way, maybe more of my physics perspective, is that it's a highly complex and connected system, right? Where humans will have an impact on the climate system, right? On the carbon cycle and therefore on the emissions. And then you have a very strong feedback loop, which is what Dave was arguing, you know, people go and see each other, you know, you run that model, that's the output. Okay, it's not consistent with the socioeconomic scenario that you had, and then you iterate, right? So we can do that in a relatively empirical way, but in reality, I mean, that's the whole system we're living in, right? It's a very complex system where humans and the climate system. So that's the Anthropocene, right? So very clearly, there's a very strong retroaction loop.
And are there any other questions in the audience in person or anyone online?
Yes. And please raise your hand, I'll bring the mic.
Hi. One area that doesn't seem to be concerned here is political impact, and because politics both affects the climate policy we have, and the migration in particular would have a significant political impact, as we see from Brexit and Le Pen and all those things. So I'm not hearing about political scientists being, or people who can predict political being included in this effort or discussion. Is that true, or do you feel it's important?
I think there's quite a few people actually working in that space now. Like conflict, for instance, is a very big area, migration. So a lot of people are thinking in Europe, like the Sahel, for instance, we expect. So there's quite a few studies suggesting that there will be like around Africa, maybe around like hundreds of millions or up to 1 billion of people like moving, like or migrating. So no, there's quite a few people actually thinking about that and the consequences of that. And that's also, you could think about like the socioeconomic impact of those things. Yeah, for sure.
Pierre, maybe you could just relate it to that question. And I think this line of questioning and others jump in. Can you speak to, how LEAP is imagining collaborations and points of synergy with other people who work in the space, right? So we're talking about the labor of doing the very specific physical computation related to climate projections, but how do we see ourselves relating to other people who work in this space at Columbia and beyond? So we're not taking on the political science challenge. That's not the expertise of our team necessarily, but how might we work with people who are working in that space, or how might they use some of the data that we're collecting? Do you see points of synergy there that might be important to highlight here, particularly for this audience?
I can offer my perspective because I sort of started as an outsider. When we first started writing the proposal, I was only collaborating with someone from the evolutionary environmental ecology, biology, the E3B department. We were looking at how to use newly emerged remote sensing data to understand tropical storms damage to the forest. So at that time, I realized that a lot of the discussion of climate change are by looking at historical data to understand whether it is happening, how much it is happening. But going forward, I think there is an important discussion to be had about how climate change how it's gonna impact our forests, our water resources, extreme weather, public health, all this, and these are important interdisciplinary areas that require people to come forward and then have really more quantitative research take place. In order for such quantitative research to take place, I think the researcher from a different area, from health, from sociology, from political science, need to understand how climate scientists create climate projection. For example, if they want to understand how policy to research for future to argue about how climate change is going to lead to certain impact on society, on health, on population distributions, if they want to create quantitative research in that direction, they need to understand how to leverage the projections that climate scientists are producing. The community Earth system model is a big community try to do that, try to create such a product. They are producing a lot of data, and this data can become valuable resources. But even I have been looking into this for my own courses, for my own research, it is not something that you just download and then it makes sense to you or automatically. So I think there is opportunity for LEAP on the education front to make the process understandable and easy to approach for other applying scientists, so that they can see the effort made by LEAP be a resource to their research. That's at least from what I see.
Thank you, Tian. We have time for more questions in the room, and just like I say in my class, if you're participating and you can't have your voice on, you can absolutely send a question in the chat. We'll be watching that. I see some chat, but I don't think it's question. I think it's more there. Okay, so actually, since we were, at the beginning of this session, we discussed about, theoretical limits and big challenges, and I said we should first learn a lot about LEAP, which is, one of the things we wanted to do. Maybe, if you have 1 minute to address my question, I'd love to hear it now. One of the reasons why, computational social science, differ a little bit is that you're constantly discussing what resource you need in order to solve a problem. And sometimes computer science show you that there are problems you can't solve. There are things that are not decidable. There are different systems that you cannot distinguish, at least if you don't have access to a particular part of the system. And those are interesting because they tell us that there are things we will never learn. We cannot predict from them. We have to take into account this uncertainty, maybe move around it. And I was wondering, especially since you, as you said, take the human as a sort of constant variable and you focus on the physics, are we seeing some of those problems? Do we learn that, what are the problems that could be the things we have to accept as unknown, and it doesn't matter how many data you have, or and that could be, I don't know, the prediction of a hurricane, or whether it's actually possible to attribute this climate change or this particular climate event to any of the causes that may be, subject to a controversy. And we could actually get to a point where we're like, well, it's actually impossible in some, condition to state that question, as opposed to place where, yes, we can, with more data, with more investment, we'll be able to turn out. That was the nature of, my question at the beginning, because that is really exactly, computational social science question. I was wondering if there's any
I think Dave has his end.
Yeah, I have one relatively obvious example, but I think it's important, which is that, we have to keep in mind just how accurate we can get our predictions, right? So if you want to know what the temperature change is going to be in the year 2050 in New York, we will only be able to tell you, hopefully relatively accurate, but with some relatively large error bar. And so we have to just acknowledge that there's natural variability in the system. Even if we knew everything perfectly about your system, there would still be considerable uncertainty in the climate projections. And that uncertainty will go down the larger the area you look at. So if you look at the whole Northeast US, it might be different. If you look at the whole US, it might be different, less uncertainty again. So I think we need to always keep in mind that we will never get, a number. It's going to be 1.6 degrees Celsius warmer in 2050 in New York. We'll never be able to say that.
We have a question from Louis Philippe. Louis, do you want to come on, Mike?
Well, I work in the startup field of trying to create heating through electricity. It's very specific, but I guess I'll try to formulate my question with other questions as it goes.
Okay.
Thank you.
Thank you.
Sandupal?
Yeah, actually, I had this question about what are the potential other except climate change, what kind of potential other applications this kind of study can give? I mean, employing remote sensing on remote sensing data, using data science techniques. What are the other potential applications that it can have, except of course climate change? Any other
You mean of
potential
using remote
applications?
sensing data?
Yes, using remote sensing data and data science techniques of machine
I
learning
would
and
say,
artificial intelligence.
I mean, from what I've seen so far, I would say the only limit is your imagination. You know, I've seen crazy applications from people actually looking at, yeah, like whatever the fleet arriving in the harbor, like to look at, yeah, for instance, during COVID-19, to actually start thinking about recession and things like that. To people looking at, you know, like the weight of a tank to actually measure the amount of oil that would be like in a tanker or something, or people looking at migration. Actually, I was in the World Economic Forum a few weeks ago, and people were actually basically using super high accuracy or super high resolution satellite to track people, you know, so they could actually allocate aids, you know, for like, for instance, UNICEF and all of those. So I would say there's a lot of applications, or people. There's a very nice French startup actually looking at methanes from space, so they could actually track that in real time, yeah, whatever, like emissions, you know, using machine learning. So I think it's just starting and it's booming, and it's just a lot of creativity right now. It's really amazing to witness, I would say. And that's not just climate change; it's really much broader than that. Yeah.
Given it, as we wrap up, I want to sort of add this point that a lot of this will be discovered through some of the conversations I think that Dave gave an example of. It's through talking with people who work in other spaces and creating opportunities for discussion where we will explore or discover some of these points of synergy and how the science and data being produced by LEAP can be useful outside of the physical components of climate projections. Can you briefly, as we wrap up, give the audience a sense of how they might engage with LEAP, keep track of what it is that we're doing, so that we can keep in touch with people who are interested in continuing these discussions?
Yes, and it's actually some question in the chat about that. I saw some passing.
Yeah, I mean, personally, I would say that, I mean, the hope is really that a lot of the data we'll have will actually made accessible, you know, especially on that cloud computing platform, you know, so that people can get access to climate data in a relatively straightforward way. And that should be really useful for many different aspects, you know, from the legal cases, you know, how much of the changes we are seeing are actually attributable to climate change, all the way to potentially, as Tian said, like extremes and changes in extremes, or they are going to disrupt, for instance, the supply chain or things like that. So I can think of climate modeling and projections being really at the core of many different disciplines, you know, moving forward, you know, so we can actually be quantifying those things more accurately. I mean, that would be the hope. And if people want, I mean, they should just get in touch with us, you know, so hopefully once we have the data infrastructure ready, I mean, then they could actually get access, and that should be relatively straightforward.
Yeah, one thing I think about, maybe some of the participants online don't realize that we are still a new center. So the website is leap.columbia.edu, and we also have a community email that you can write to leap@columbia.edu. We are putting together a mechanism for people to join our newsletter. We don't have a current newsletter yet. It's forthcoming. So if that's what's on your mind, you haven't missed much. Like this is ongoing. This is going to be the next 10 years for the center and beyond. So we are very much hoping to be in touch. When we have the sign up ready, we will definitely share through the DSI newsletter to reach all of you.
And there's even a boot camp for students to attend, I know, in May. So events like that to sort of, you know, allow you to enter the field.
In year 2, we have planned for a hackathon. So
there you go.
Yeah, we're just getting started. Thank you all please check out the website and email us upcoming announcements about postdocs and other research positions and events, both community specific to Colombia and beyond are posted on the website. And we really appreciate you joining us today. And thank you to my LEAP teammates, as well as my computational social science co-directors for helping to pull this together. I think this is really valuable. Thank you, everyone.
And Alexia as well. Thank you so much.
Yes, thank you, Alexis.
And Alexis, thank you. Thank you, Alexis. We really appreciate it.
All right.
Thanks so much.
Good evening, everyone. Good afternoon.